Okay. We have been talking about wavelet transform now for a few classes. The way we started discussion of the wavelet transform was basically taking this prototype mother wavelet or the wavelet function and thinking of it as time, basically dilations of it and time shifts of that, which gave us an understanding of wavelet transform in terms of time and frequency analysis. We looked at it in terms of how the wavelet transform tiles the time frequency plane. Then we looked at how to make the wavelet transform orthogonal. We saw one of the main properties we saw was if any wavelet transform satisfies the two-scale relationship that we saw earlier, then we end up with an orthogonal wavelet transform. There is another way of approaching the wavelet transform, which is based upon the view of multi-resolution analysis. You can start from that discussion, and I'll explain what multi-resolution analysis means, but you can essentially start from that discussion and derive wavelet transforms from that. And while doing that discussion, we also end up with very fast ways of computing the wavelet transform. So today's lecture will be primarily focused on multi-resolution analysis. We'll be using a lot of concepts about vector spaces and the projections of signals onto subspaces that we covered a long time ago. So it will be good to recall some of those things. So multi-resolution analysis, which I will abbreviate as MRA, we are going to focus on multi-resolution analysis of the, first of all, one-dimensional space, the real space and space of all finite dimensional signals. Okay? And you can define the multi-resolution analysis in a very abstract setting without ever talking about wavelets, even though orthogonal wavelets give rise to these multi-resolution analysis properties. But we'll start with just the general definition of multi-resolution analysis. It's defined as follows. It's given by a few properties. So we are in L2R, we are given signals which are finite energy. They are defined on the real line. And the first property of multi-resolution analysis is called embedding, which means that you look at this L2R, which is the biggest space that you have available, and you actually divide it into smaller and smaller pieces so that every piece is a subset of the bigger piece. It's like those Russian dolls, if you have seen those, where you pull open a doll and inside it is another doll with a smaller size. So it's very much that concept that we have a sequence of embedded vector spaces or subspaces L2R such that each one is a subset of another one, and it's an infinite number of those things. So while Russian dolls, maybe there are like 5 or 10 max, this thing just keeps on going. So we have that, for example, there's V2, which we will call at scale J. So this 2 will use the variable J for that. That is a subset of another subspace. That is a subset of another subspace V0, subset of V minus 1, V minus 2, and it keeps on going. Okay. So effectively, you have this picture that you have V2, which is a subspace. A subspace is nothing but a set, right? So we can think of this as a V2. And this is itself contained in a bigger subspace, V1. And V2 contains itself other smaller subspaces, so we never end. And this V1 is contained itself in an even bigger subspace, V0, and this thing keeps on going too. Okay? So that's the most important property of the multi-resolution analysis, that you have this sequence of subspaces. Okay? Now, what do these subspaces, what properties these subspaces need to satisfy? Those properties, when you look at them together, they are essential to defining the multi-resolution analysis. So the second property is completeness. It's called upward completeness. I'll just call it completeness 1, which is that if you keep on going up and up in the hierarchy, right? So v minus 1, v minus 2, you keep on going up. And if you look at the largest one, of course, there are an infinite number of these subspaces. But if you look at, take the limit, and we are not going to go into the details of what does this limit technically mean, but just try to intuitively think of like you go to the last end of these subspaces, and that is equal to the whole space. So if I take limit of j going to minus infinity of v of j, okay? So I go to effectively, if you want to think of it, v minus infinity, which is the largest subspace, everything is contained in that, that is equal to L2R. Okay? So eventually you have a subspace which covers all possible signals. On the other hand, so this is the case when we are going in this outer direction, right? You keep on expanding and expanding, and you eventually expand enough that you cover everything. The other direction that you can go in is inward. You keep on going smaller and smaller and smaller, and the idea is that if you look at the intersection of all of these subspaces, that the intersection only contains the zero signal. Okay, so we already know the property that every subspace has to have a zero element. Right? So every subspace has zero, so the intersection can't be empty. And what it is saying is if you take intersection of all of these subspaces v of j, you only get the zero signal. Okay, it's zero everywhere. So effectively, the size of these subspaces are at some level shrinking, and eventually you end up with a subspace which converges to just the zeroth element. Okay? Now all of these are required conditions, but are more to make this multi-resolution work. A more interesting condition is scale invariance. So scale invariance is really the Russian doll analogy, which is you can have, in general, if I don't give you the condition of scale invariance, you can have subspaces which are contained within each other, but they don't satisfy the Russian doll analogy in the sense that they don't have necessarily the same shape. Right? So scale invariance effectively imposes this condition that every subspace effectively looks like a smaller or a bigger version of the other subspace. Okay. So scale invariance says that Vj subspace, they are just scaled versions of each other. And what it mathematically would mean is that if x of t, if you have a signal x of t that belongs to this one subspace Vj, and if you scale that signal by a factor of 2 to the m, let's say, then that scaled version of the signal has to live in v of j minus m. So to understand it better, if you think about it, that if we can talk about two cases, the first one is m is bigger than 1. So if m is bigger than 0, if m is bigger than 0, then what are we doing to x of t? we are compressing it. Right? We are compressing it. We are making effectively a finer version of the original signal. Okay, it's like we had a big doll and we compressed it to a smaller doll. It's a finer version of the bigger piece, right? If m is greater than 0. And what this then says is that that finer version has to live in another subspace, which is v of j minus m. So if m is greater than 0, x of t is being compressed. And this means the finer version x of t, which is x of 2mt, lives in the refined subspace v of j minus m. Similarly, if m is less than 0, then x of t is being stretched. So we are now looking at a blown up version of this x of t. So x of t is being stretched. And this means the coarser version of x of t lives in the subspace that is now below Vj, right? So now m is less than 0, so j minus m is bigger than j, okay? So if the index is bigger than the other index, then that subspace is being contained in the previous subspace. So the coarser version of x of t lives in more coarser space v of j minus m. Okay? So if m is 0, then what you have is that v of j minus m is a subspace, and that lives in v of j, right? So when we stretch signals, they live in the smaller subspace, and when we compress signals, they live in the bigger subspace. Okay? Okay. And the other property is, the fifth property is shift invariance. So scale invariance says that when you alter the scale, the new version lives in another subspace, which will either contain the previous subspace or be part of the previous subspace. Okay? Shift invariance says that if I shift my signal by some multiple of 2 to the j, then that shifted version lives in the same subspace. So all shifts of multiples of 2 to the j of a signal lie in the same subspace. So if I have x of t, which lives in v of j, then this means that x of t minus 2jk for any k still lives in the same subspace for all k. Okay? So if I shift it, it's not going to change anything. And the last property is that there is a sequence of functions. We have phi of t belonging to v of 0 such that so all possible shifts, all integer shifts of phi of t form a basis for V0. Okay. Now this is just the abstract, these 6 properties are abstract properties of what, under what conditions you will call something a multi-resolution in the case of L2R. Okay. And it will turn out that this phi of t actually ends up being just like the scaling function of any wavelet transform that we had seen before. Automatically, these properties will imply that. So we'll come back to what do these properties mean, but let me just give you an example that all of you should be very, find it very easy to relate to, which is called, you can think of Shannon multi-resolution analysis or Shannon approximation, which is just given by basically thinking of your L2R as successive approximations of band-limited functions. Okay, so we can say in the multi-resolution analysis of that, we can say that V of j is the space of all functions x of t in L2R whose Fourier transform x of j omega is supported, and supported means it's non-zero only, on 2 to the minus 2 to the minus j pi to 2 to the minus j pi. Okay. So you have, for example, if I think of V0, what it is saying is that my V0 space, and we already know the space of all band-limited signals, that is a subspace, right? We have done that long time ago. So what this is saying is that the space Vj is defined as the space of band-limited signals, but the band is a function of your little j. So V0, for V0, your band goes from pi, minus pi, to pi. And so that is your V0, and from that you can compute the basis of this subspace. Right? What's the basis of band-limited signals? It's all possible shifts of the sinc function. So phi of t in this case is simply sine pi t over pi t. Now you can ask, what is V1? So what will be V1? It will be contained within V0, right? And it will go from the Fourier transform of V1, that will go from minus pi by 2 to pi by 2. Okay, so it's clear that V0, right, which is the space of all band-limited functions from minus pi to pi, that contains also all band-limited signals that are between minus pi by 2 to pi by 2. What will be V2? V2 will be minus pi by 4 to pi by 4. V3 will be minus pi by 8 to pi by 8, and so forth. Right? And what will be V minus 1? V minus 1 will be simply minus 2 pi to 2 pi. So it will be all possible band-limited. I am drawing it as flat. It effectively means that they are all supported on this region. Right? So effectively, and V minus 1 contains V0, and V0 contains V1. Right? And you can see that as j goes to minus infinity, you are looking at now band limited signals whose band extends from minus infinity to infinity. And that's the space of all possible functions. Right? And if you start taking the intersection of all of these subspaces, then that will be just the zero function. Right? So this is sort of the most trivial example of the multi-resolution subspaces that you can think of. They satisfy all the properties that we have talked about. Of course, take any subspace Vj and shift it by 2 to the jk, right? If you take again, we have done that. Band limited spaces are shift invariant. If you take a signal and you shift it, you are not going to change its bandwidth. So all the previous things that we have learned about, you can just apply here and easily argue that these spaces indeed form a multi-resolution analysis of L2R. Okay. Now, think of what is happening as you go from V0 to V1. You are looking at smaller and smaller bands. Effectively, what you are saying is that I am looking at more and more low-pass approximation of my original signal. You are throwing away, as you go from Vj to, let's say, Vj plus 1, what are you doing? You are throwing away high-pass frequencies, at least in this example. And we'll see that in general, multi-resolution analysis indeed does exactly that. But in this example, what are you doing? Your previous, like V0 was minus pi to pi. If you go to V1, that's minus pi by 2 to pi by 2. And you can think of it that a signal within V0, it has lost the details or high frequencies when it goes to V1. Okay? Because we have thrown away all the high frequencies. In our discussion of multi-resolution analysis, we will be not that rigorous, and so we'll work with, for example, the case where phi of t makes an orthonormal basis. So going forward, we will assume that all possible integer shifts of my phi of tk form an orthonormal basis I'll abbreviate that by ONB for V0. Okay. Now, we won't formally prove that, but I'll just try to give you an intuition. Since phi of t minus k is an orthonormal basis for V0, so what ends up is that the dilated versions of this and shifted by the right amount end up being the orthonormal basis of another scaled subspace. So all possible combinations of phi of t minus 2 to the minus jk over 2 to the minus j, where k belongs to z, ends up being an orthonormal basis for v of minus j. Okay. And I'll just give you an intuition for this. We won't formally prove that. So let's assume that x of t belongs to v of 0. Okay. What does it mean that phi of t minus k are orthonormal bases? It means that every signal in V0 can be represented as a linear combination of the basis functions. Right? So since phi of t minus k is an orthonormal basis, this implies that x of t can be written as a linear combination of my basis functions, t minus k. That's just the definition of the orthonormal basis. Now, we know from the property of the multi-resolution analysis that if I shift x of t by 2 to the j, if I scale it by 2 to the j, right, then this belongs to v of minus j. So the multi-resolution analysis property says that if I shift it by 2 to the j, so it's 0 minus j, right? It's due to the scale invariance property of the multi-resolution analysis. Now, if I do the shifting, that means I can do the shifting of this expression. So that is x of 2 to the j of t, which is equal to k belongs to z, a of k, phi of 2 to the j t minus k. Okay. Now I can just rewrite that is ak phi of t minus 2 to the minus jk over 2 to the minus j. So in a sense, you can say that, again, there are some holes in this argument. I want you to be aware of that. But in some sense, you can say that this function, which belongs to the v to the minus j, now can be represented as a linear combination of these functions. Okay. So if every function can be represented as a linear combination of a collection of functions, then that collection is a basis for that space. That's just the definition. So indeed, then we can say that this collection is a basis, and the orthonormality of this follows because of the orthonormality of phi of t. Proving that is rather simple. Okay, so we'll take that for granted too, that if we are given phi of t, some function which forms an orthonormal basis for v0, then we know all the basis for other subspaces. So going back to the example of, for example, Shannon multi-resolution analysis, since we know that sinc is a orthonormal basis for band-limited functions from minus pi to pi, just a scaled version of that sinc will be an orthonormal basis for band-limited signals from minus pi by 2 to pi by 2, for example. So just scalings of phi of t give us orthonormal basis for all the other subspaces. Okay. So knowing subspaces for any one scale is enough to know basis for any other scale. Now, in the previous discussion that we had about wavelet transform, we said that the wavelet transform, if it has the scale, if it has that two-scale relationship, then it ends up being an orthogonal wavelet transform. It turns out that the definition of multi-resolution analysis itself gives us that two-scale property. Okay. So the two-scale relationship is an immediate consequence of the scale invariance condition. Two-scale relation is a given because in multi-resolution analysis because of the scale invariance property. So what does that mean? We'll just use a couple of properties to prove that. So first of all, phi of t belongs to v of 0. And because of the multi-resolution aspect, anything that is in V0 is also in V minus 1. V minus 1 is a bigger subspace than V0, so anything that is in V0 has to be part of V minus 1, so phi of t also belongs to V of minus 1. Now, V of minus 1, we said that scaled versions of phi of t are orthonormal basis for different subspaces. So what is the orthonormal basis for V minus 1? That is just the scaled version of phi of t. So that's phi of t minus 2 to the minus 1 k over 2 to the minus 1. Okay. K belongs to z. So we have that number one, we have a signal which belongs to V of minus 1. And we know the orthonormal subspace for V of minus 1. So by the definition of basis, we should be able to write phi of t as linear combination of the scaled version of phi of t itself. Because these are the bases, and this is the function that lives in the span of that basis. So this means that phi of t, there exist some coefficients such that phi of t is given by g tilde k phi of 2t minus k. Right? I can simplify that and write that as phi of 2t minus k, which is the two-scale relationship that we had discussed in the last class. Phi at scale 0 or 2 to the 0 is given by linear combination of phi's at scale 2. And we will find out what these g tilde k's look like. Now, in keeping with our earlier notation, we want to actually write it as that normalized version. If you remember, we don't not only do the dilations, but we also divide it or multiply it by the right factor to make sure that everything remains orthonormal. So I can always write g tilde k equal to square root of 2 times another factor g of k. And so I'll just write that as square root of 2, k belongs to z, g of k phi of 2t minus k. Okay. Or by doing that, I can just write k belongs to z, g of k. I can define phi of scale 1 and shift k of t, where phi 1k is defined as square root of 2 phi of 2t minus k. So it's the same notation we are following. We used to define that phi of, for example, j comma k is simply 2 times square root of j phi of t minus 2 to the minus jk over 2 to the minus j. Right? So I just want to write it in the same way that we had wrote the two-scale relationship earlier, or the things earlier. Okay. So just by the fact that I say I have a multi-resolution analysis of L2R, I get this two-scale relationship for free. Okay. So now we can talk about, we know all the, if we are given orthonormal, if we are given multi-resolution analysis, we know now all the orthonormal bases for different subspaces, and we can ask the question, given any function, how do I express an approximation of that function in that subspace? Okay. So the idea in multi-resolution analysis is that you are given some x of t belonging to L to R. And you can ask the question, I want to compute different approximations of this function at different levels, at different scales, okay, or effectively different resolutions. And how do we compute the approximations? We just use the projection formula. So these are Vj's is a subspace. We know that. Number two, we know that phi of t minus 2 to the minus j k over 2 to the minus j is an orthonormal basis of Vj. So if I am given an xt, I can ask myself, what is the approximation or what is the representation of that signal in that subspace? And what is that approximation? That is simply given by the projection formula. So if I want to compute projection of my x of t on Vj, that is simply given by inner products of my x with the basis functions, I'll call them phi jk, times phi jk t. K belongs to natural numbers or all possible integers. And these inner products are given by, in L2R, we have seen that these inner products are given by simply the integration. So I can compute the approximation. So these are called approximation coefficients. At scale 2 to the j. So I can write them, I'll denote them by AJN or AJK. They are simply given by, I'll just stay with AJN, they are given by the inner product between x and phi jn, which in L2R is defined as the integral x of t 1 over square root of 2 to the j phi of t minus 2 to the j n over 2 to the j dt. Okay, I think this should be plus here above, and there should be 1 over square root of 2j here. Okay. So, and we also know that the integration can be simply computed as, this integration, this inner product can be simply computed as convolution of x with another function and then sampled at the right instance. So if I just express it in the right way, that is minus infinity to infinity x of t 1 over square root of 2j phi of minus 2jn minus t over 2j dt. Okay. So then you see that this is nothing but the convolution with a time reversed version of phi. So I can define phi bar j of t as square root of 2 minus j phi of 2 to the minus j t minus 2 to the minus j t, and This means that AJN is simply equal to X convolved with phi bar J, and then I sample it at time 2JN. This, however, should be, this should be minus and this should be plus though. So this is the general notation that I'm using. So yeah, so this should be 2 to the minus j square root, and whatever j is here should be the exponent on the 2's here, and then this thing has the negative exponent. Okay, so the general idea of multi-resolution analysis, if you talk about, for example, once you have defined the phi of t, which gives rise to these v0, v1, v minus 1, you can then start asking about computing the approximations of that signal at different scales. And as you change your scale, as your scale goes from 2 to the, let's say, closer to minus infinity to 2 to the infinity, you are basically losing details. Okay, so this is an example where your x of t or f of t, this is your function. It's called, here in this example, it's called f of t. And what you are doing is computing their approximation coefficients a, j, n at scale 2 to the j. Okay. And those coefficients are just computed by what we saw earlier. A, j, n is simply given by x and phi j n. Okay. And they can be computed by simple convolution. So this is the highest scales, and the highest means j is the lowest. Right? So this is the finest scale. So 2 to the minus 2 to the j with j equal to minus 9. So you have the most details of your function. I mean, if you keep on taking j smaller and smaller, this will start resembling more and more like this function. Right? And if you were to express the entire approximation by multiplying it with phi jn's, which in this case are cubic splines, then you will start getting more and more of this function exactly. But as you now go down the scales, you go from j equal to minus 9 to minus 8, which is a smaller subspace, which effectively is you are losing some of the details of your function. And now you start sort of getting coarser and coarser as you go up in this version, so much that when you go to 2 to the minus 4, you're only getting a few of the details of the function. And those details correspond to, for example, you have this sort of jump here, you are getting that, and so forth. So that's sort of the general view that you should take of things, right? That you are going down the scale, you are going from 2 to the minus 9 to 2 to the minus 4, and you are losing details of your function as you go down. Now that's an approximation. What it can help you is, for example, if you want to think about in terms of communications, the multi-resolution analysis is at some level great because of the fact that you still have an overall sense of what signal you started with. So if your communication bandwidth, if you want to think of it in that terms, allows you to transmit only certain amount of bits, right? You can go down to a scale which you will lose some details. You can go to a scale of like maybe 2 to the power of 3 or 2 to the power of 4. Right? Your j can get larger so that you can transmit within the bandwidth that is allocated to you. And if someone says, well, I have now more bandwidth available, then you just go to a different scale. You go to a you go to a more finer subspace, and effectively you have not lost anything. You still have some sense of what was being transmitted. You don't get that fine details. Okay, so that's the basic principle behind the multi-resolution analysis. Okay, you are getting a coarser view. As your J gets large, you start getting more finer details as your J gets small. Okay, and if your J gets too small, you almost get back to your original signal. Okay, what we want to do now is understand a few of the properties of what does that phi of t look like and how can that be generated. And it will. So the multi-resolution analysis is completely described by the right phi of t, which I'll keep on calling scaling function. Okay, but this scaling function itself is completely described by a filter. And we'll try to derive, well, we won't explicitly derive, but we'll try to look at some of the properties of that filter. So we have from the two-scale relation that phi of t is a linear combination of the phi at the scale of 2 to the minus 1. So I have g of k belongs to z, phi of 2t minus k, square root of 2. Now I can take Fourier transform of that, assuming that it exists. And since Fourier transform is linear, I get k belongs to z, g of k Fourier transform of phi of 2t minus k. Now, if I write the Fourier transform of phi of t as phi of j omega, so this is nothing but, so this is Fourier transform phi of t minus 2 to the minus 1 k over 2 to the minus 1. So this is Fourier transform of a scaled and shifted version of phi of t. And from the Fourier transform property, that is easy to relate it to the original Fourier transform. What does scaling in time do? It does scale, it only scales in frequency. What does shifting in time do? It gives rise to a phase shift in frequency. So the Fourier transform of this f of phi 2t minus k is simply half phi of j omega by 2 times e to the minus j k omega over 2. So this means that I can write the Fourier transform phi of j omega from here. That is equal to 2 to the minus 1 half. So I have this square root of 2 divided by 2. That's 2 to the minus 1 half. Phi of j omega by 2 and summation over k, g of k, e to the minus j omega k by 2. So I've pulled this outside the summation because it does not depend upon k. So that is equal to 2 to the minus 1 half phi of j omega by 2. Now, if I look at this expression, and this g of k is a sequence. I'm summing over all the sequence and multiplying it by e to the minus j omega k by 2. What is that thing? So we have now seen that so many times, right? If I think of my g of k as a sequence, what is the, it has a Fourier transform, discrete time Fourier transform. What is that? Summation of k g of k e to the minus j omega k or omega n. Dummy variable doesn't matter what it is. So if I compare this to this, it turns out that this is nothing but a scaled version of the discrete time Fourier transform of my sequence g of k. This is nothing but a scaled version of g of e to the j omega. So this is just g of e to the j omega with little omega replaced by capital omega by 2. So this means that I have written, not worrying too much about the mathematical pitfalls that you can go into. We have written the Fourier transform of my scaling function as a recursion that is equal to 2 to the minus 1/2 g of e to the j omega by 2. Now we can apply this recursion. We can apply this recursion one more time, right? So if I now replace in this recursion formula, if I replace omega by 2, I get that phi of j omega by 2 is equal to phi of j omega by 4 times 2 to the minus 1/2 g of e to the j omega by 4. And I can keep on applying this recursion. So I can collect all of that together, and I can say that phi of j omega, that is, for example, equal to phi of j omega over 2 to the L times, so this is L equal, this is symbol for multiplication, right? 2 to the minus 1/2 g of e to the j omega over 2 to the little l. Okay. So all I'm doing is applying this recursion again and again and again. Okay. Now, one thing we'll assume is that, which is what we learned about the scaling function, we'll assume that the phi of t corresponds to a low pass filter. So the assumption we'll make is that phi of t is a low pass filter, which means that the Fourier transform of phi at omega equal to 0, okay, that cannot be equal to 0. And in fact, we'll just assume that that is equal to 1. Okay? So it's a low pass filter where at the 0th frequency it is equal to 1. So in that case, I can write my phi of j omega as limit L goes to infinity phi of j omega over 2 to the L summation L equal to 1 to L 2 to the minus 1/2 g of e to the j omega over 2L. Okay. Now if L goes to infinity, the argument of this thing, this is going to 0. Right? So from the above assumption, we have phi of 0 equal to 1. Right? So if L goes to infinity, this argument is going to 0, and this whole term is going to 1. So what we get is that L equal to 1 to infinity 2 to the minus 1/2 g of e to the j omega over 2L. That is phi of j omega. So this is one of the most important relationships that we use to, for example, come up with scaling functions. We'll study more properties of the sequence Gn. What effectively happens is that you start your multi-resolution analysis not with phi of t, but rather you start your multi-resolution analysis with a filter G. Okay? And that filter gives rise to your scaling function. So when you do, for example, wavelet analysis and you read about discussion of that, there will always be discussion of wavelet filter or scaling function filter. That is the filter that it is referring to. So let's find out what are the properties of this filter, because we'll keep on talking about this filter and eventually we'll forget about everything else, and the only thing we'll care about is this filter. Okay? And by filter, I mean the sequence G of k that defines, or G of n that defines our two-scale relationship. We can think of any sequence as the impulse response of a filter. So we'll keep on talking about it as a filter. Okay, so this is our recursive relationship that relates the scaling function to the filter Fourier transform. And previously we talked about phi of j omega equal to 1 for omega equal to 0. So now input in this relationship, let's call that double star. Input omega equal to 0, we get that 1 equal to L from 1 to infinity 2 to the minus 1/2 g of e to the j0. So there is an infinite amount of products. We are multiplying this term infinite times. The only way that this can be equal to 1 is if g of e to the j0 was equal to. So if g of e to the j0, which is simply g of 1, if that was bigger than square root of 2, if that was bigger than square root of 2, then what happens? Then this term in the square, in this block region, that will be bigger than 1 or less than 1. That will be bigger than 1, and if you multiply an infinite amount of numbers which are bigger than 1, you are going to blow up, right? So if this was bigger than square root of 2, then actually you would get that phi of 0 goes to infinity, which of course is not in keeping with our assumption that we started with. Similarly, if g of e to the j0 was less than square root of 2, then this term will be equal to, in that case, less than 1. And now you are multiplying an infinite amount of terms which are less than 1. What do you get? That will converge to 0. So in that case, phi of 0 will go down to 0. So the only way that you can have this phi of 0 equal to 1 is if g of e to the j0 was equal to square root of 2, in which case 2 to the minus 1/2 g of e to the j0 will be equal to 1. And you can multiply 1 infinite times and you'll get back 1. So if you have this relationship, then the g has to have at little omega equal to 0, it has to have value square root of 2, which makes it what kind of a filter intuitively? So at 0th frequency, it is non-zero. So g of n itself ends up being g of k, or g of n, corresponds to the impulse response of a low-pass filter. Okay. Now, that is one property that we'll have to remember. It's effectively that the relationship between the scaling function and the filter is that filter is low-pass filter. There is another property which we won't prove, which is the conjugate mirror property. So g of, let me start calling it a sequence, g of n is a conjugate or quadrature mirror filter. And what that means is that if you look at g of e to the j omega squared plus g of e to the j omega plus pi squared, that is equal to 2. Okay. So you take your filter's Fourier transform and you shift it by pi. So previously it is centered at 0. Now you shift it by pi. Okay. You center it at pi, and that when you do that shift and you square the amplitude, you get back a constant. Now, if you think of it, since our e to the j0 is equal to square root of 2, then this means if I plug in that little omega equal to 0, what do I get? I get 2 plus g of e to the j pi square equal to 2, which means that g of e to the j pi equal to 0. So the filter at little omega equal to g of n at little omega equal to 0 is square root of 2, and at little omega equal to pi is 0. So it is definitely not an all-pass filter. Okay. So rather than defining the multi-resolution analysis from the perspective of starting with a phi of t, in reality what happens is you define multi-resolution analysis from the perspective of a filter. What you do is you start with a filter g of n, and you make sure that it satisfies 3 properties. Okay? We are not formally proving any of these facts. I'm just trying to motivate these things and then moving forward. So the first property is that at little omega equal to 0, the filter response is square root of 2. The second property is this conjugate mirror property. that is equal to 2, which automatically implies that the filter response at pi equal to 0. Okay. And the third property is, which we have not even touched upon intuitively, that the filter is non-zero between pi by 2 and minus pi by 2. So g of e to the j pi is not 0 for any omega between minus pi by 2 and pi by 2. If you start with a filter that satisfies these properties, then you can define a scaling function phi of t as the inverse Fourier transform of this infinite iteration, L equal to 1 to infinity 2 to the minus 1/2 g of e to the j capital omega over 2L. And if this, of course, limit exists, right? And we won't go into those technicalities. Assuming that this limit exists, if you define phi of t from a filter which satisfies these properties, then it is guaranteed that to define a multi-resolution analysis. Okay. Which means that such a phi will give rise to basically successive approximations of your function. Okay. We are still some time away from talking about basically the wavelet aspect of it, because we still have to define wavelet from this definition. Okay. But up to this point, the thing is, if you start with a filter g of n, which satisfies this property, and the filter ends up being a low-pass filter. If you start with such a filter and you define phi of t in this manner, you are guaranteed to get a multi-resolution analysis. So for example, rather than talking about the Haar scaling function, okay, you can actually define that from the perspective of the filter. So in the case of Haar, so Haar multi-resolution analysis is defined by, for example, g of n equals 1 over square root of 2 for n equal to 0 and 1 and 0 otherwise. So that's like, you can talk about going to Haar wavelet from this filter g of n. Okay. So we'll end here this class. In the next class, we'll basically talk about what does this conjugate mirror property or conjugate mirror filter exactly mean, and then how do we define the wavelet function that from the multi-resolution analysis. Okay, because that is still the missing piece. And after that we do that, what we want to look at is how do we compute the wavelet approximation and the wavelet coefficients using these filters. What role do these filters play in computing the approximation and the detailed coefficients of wavelets?